Okay, I think we can start.
Oh, okay.
Yeah, welcome everyone. Today we have our last talk in this semester, and we are happy to have Shota Komatsu, and he will speak about large charge n equals for super young mass. So please start.
Okay. All right. Thanks a lot for the introduction, and thanks for giving me an opportunity. This is the first time for me to visit Moscow. I actually visited Russia once, but only to Vladivostok. So, well, I hope I will have a chance to really visit like in person Moscow very in the near future. So today I'm going to talk about something that I was doing and which is about large charge and n equals 47 mils. So the theme of the talk is basically the large charge and holography for n equals 47 mils. And a kind of questions that I want to kind of address in this talk is the following. So it was recently realized that operators with large global charge in conformal field theory often admit a universal description called large charge effective field theory, which I'm going to explain in detail soon. And the question that I want to address or partially address is what's the relation between the large charge EFT and holography? And I want to make some comments about it. Okay, so well, if you have any questions or comments, please interrupt me at any time. And this is the plan of the talk. And first I'm gonna, well, my talk is going to be divided into 3 topics. First, I'm going to talk about large charge and holography. And this is mostly based on unpublished results and partly based on discussions with Clay Cordova, who is in Chicago, and Frank Coronado, who is in McGill. And second, I'm going to talk about double scaling limit and some central extension of the symmetry. And this is based on the work in progress with Joao Caetano in Simon Center and ITMP 1 in Harvard University. And finally, I'm going to explain what we can learn from large charge expansion and make use of that to holography. In particular, I'm going to talk about correlation functions of deep brains. This is based on the work that I put out in March together with Pei Heiyan and Junba Wu, both are at Tianjin University, and Yunfen Zhang, who is a postdoc at SYM. Okay, so let me start. So the first topic that I'm going to address is the large charge in holography. So let me just first remind you the basics about ADS-CFT. So which is operators and their duals in ADS-CFT. So as we know, the ADS-CFT correspondence relates operators living on the boundary of the ADS spacetime, which is the operator of some conformal field theory, to some excitations in ADS spacetime. So the schematic picture is like this. So you insert boundary, you insert the operator at the boundary of ADS, and that's going to emit some excitation. And for example, for concreteness, let's consider the UN n equals 4 to 10 mils in the large N limit. And we know that's going to be dual to string theory, which is quantum gravity, defined on ADS 5 times S5 spacetime. And what's important for my talk is that depending on the dimension of the operator actually admits a different dual description. For example, if you consider operator with dimension of order 1, then that's going to be dual to graviton or light matter field in ADS spacetime. Whereas if you consider operator whose dimension is of order n, and that's going to be dual to d brains. And finally, if you consider operators with dimension order n square, and those operators are heavy enough to deform the geometry, so the dual spacetime is no longer ADS 5 times S5. So the typical like a dual geometry of such heavy operators is, as we know, is black hole, which comes with horizon. But there are also some other geometries which doesn't come with horizon. The famous example is what's called LLM geometry, which is studied by Lin Looney Maldacena, and which is known to be dual to heavy half BPS operator in n equals 4 to 10 mils. And in between these two, there are like operators whose dimension grows if you increase the Hooft coupling, but it doesn't scale as n. And those excitations those operators correspond to stringy states. Okay, so So, or massive string excitations. And one simple way to get operators with large dimension is to consider operators with large other quantum numbers, for example, spin S or U1 charge J. And the reason why this is a simple way is because of some unitarity condition or some selection rule or BPS bound, there is always some like a relation like this. So the dimension of the operator is often larger, must be larger than the spin of the operator or some U1 charge of the operator. So if you increase these quantum numbers, then you automatically get the operator with large delta. And in my talk, I'm basically going to focus on the operator with large U1 charge. So that's the next topic I'm going to explain. So recently there has been a lot of progress about understanding large charge sector of generic conformal field theory, which was triggered essentially by these two papers. And so one of the key result in this analysis or in this like a line of research is some semi-universal prediction of conformal field theory data in the large charge limit, which basically predicts that the dimension of the operator, or like a minimal dimension of the operator whose charge is J, should scale like J to D over D minus 1 when J is very large, where J is the U1 charge of the operator, if you consider CFT defined in D dimensions. And actually, it is very easy to derive this formula. So let me just explain how you derive it. So the idea is to first consider conformal field theory defined on the cylinder. So you consider like a radial quantization and view this radial direction as time. And then like the space is SD minus 1. And in particular, we pick the radius of this sphere to be R. Then, just from the dimensional analysis, you conclude that the state due to this operator should have energy which is delta over R, whereas charge of the state is the same as the charge of the operator, which is J. So let's now further assume that.
Sorry, can I ask something?
Yes. Yes.
Where do you get this U1? So let's say you have n equals 4 super young mills.
Okay, so first of all, in this slide, I'm not assuming like we are talking about n equals 4 super mills, like it's kind of like a prediction for generic conformal field theory with U1 charge. In the case of n equals 4 super mills, we have SU for R symmetry. So we can just like pick one Cartan direction and declare that it's U1.
Oh, okay, thank you.
Okay, so let's now try to derive this. So let's further assume that this large charge state with energy and charge are given by this becomes in the large R limit a state on a flat space with finite energy and charge density. So the idea is that originally I was considering the state defined on a cylinder, but in the limit where R is infinite, it should become some state on the flat space. And then assume that this state goes over to finite energy and charge density state. And if you accept this assumption, then in this limit, you can just express the energy in terms of energy density times RD minus 1, because this is the spatial volume. And you can also express charge in terms of charge density, which is of order 1 times RD minus 1, which is again spatial volume. And if you combine this and this and this and this, then you can easily conclude that dimension of the operator should scale like R to D, which is actually J D over D minus 1. And as you can see, that this is actually like a very, very universal prediction, and which is true as long as this assumption is true. And you can actually get the same scaling also by analyzing ADS RN black hole, which describes some very, very heavy operator with U1 charge in some holographic setup. Okay, so this was just like a large J limit of the delta, and of course, like as you can see, that to derive this, we didn't really need to like develop some effective field theory. It was just like a dimensional analysis. But if you want to understand 1 over j correction, then because of this formula, in this formula, 1 over j correction is related to 1 over r correction. So it's essentially like a corresponds to like a higher derivative correction or like a correction with respect to the size of the sphere. So because of that, like 1 over j correction can be analyzed by like doing some effective field theory techniques. So for instance, in 3 dimensions, people actually like analyze what kind of terms that you can write for the large charge effective field theory. And they wrote down like, for example, the 2 leading terms. So this is under the assumption that the low energy degrees of freedom is given by some like a single massless scalar. And using that, they made a prediction that the leading answer is what I explained in the previous slide. And there is a correction, which is j to 1/2. And furthermore, and the coefficients of these 2 factors depend on the coefficient of these 2. But the point is that once you fix these coefficients, then you can make prediction to the next term, because there is no EFT Lagrangian which directly corresponds to this term. So you can what you just need to do is to like first fix the coefficients and then do the loop expansion using this Lagrangian. So this gives you like a very solid prediction, and you can indeed like check it by, for example, doing some numerical analysis of the lattice model. And furthermore, people also show that this EFT approach is also applicable to the determinant dimension delta for excited states. So previously, I was only talking about like a dimension of the operator, which has the minimal dimension for a given charge. And you can also determine the OP coefficients. And furthermore, some of the results can be reproduced from a conformal bootstrap, as shown in this paper. Okay, so all right, so this was kind of like a very, very quick review of what the EFT of the large charge was. And however, if you know the superconformal field theory, then like as soon as I show this formula, then you immediately say that this must be incorrect. And indeed, it's incorrect for superconformal field theory. And because we know that in superconformal field theory, there are BPS states whose dimension scale linearly as j, which is much, much smaller than the prediction I made in the previous slides. And so the prediction that the delta minimum is like this is actually wrong for superconformal field theory. But there is actually a very, very simple way to understand why this is the case. So what's going to happen for the superconformal field theory, and in particular for the BPS operator, is that if you consider BPS operator again on a cylinder and take a large R limit, then it goes over to a state on the flat space with 0 energy density, but finite charge density. So this is normally not possible if you just consider like a generic quantum field theory, because if you want to kind of like have a finite density state, then you need to kind of put some like finite number of like electrons and so on. And that often like gives rise to some finite energy density as well. However, in supersymmetric theory, we often have some flat direction or like a vacuum manifold. So like there is some like a family of vacua. So by considering such states, you can act, by taking into account those flat direction, you can actually construct a state whose energy is actually exactly 0, but the charge density is non-zero. For instance, one way to construct such a state is to consider this kind of state. So here I'm considering some like a vacuum state whose expectation value of complex scalar field, which is charged under the U1, behaves like a V times e to I theta, and I put e to I j theta factor and then integrate over theta. Of course, this is not really a correct thing to do in the flat space limit, because like those states with different theta are in different super selection sectors. But because we are actually, precisely speaking, not in the flat space limit, because we are still on a sphere, it's it's safe to consider this state, and that is going to give you some states with finite charge density with energy 0. And this also suggests that in the case of superconformal field theory, the large charge effective field theory that I discussed in the previous slide is now replaced by the effective field theory describing this flat direction, which is basically like in the case of n equals 2 superconformal field theory, those are Coulomb branch effective field theory. And in fact, people actually analyzed, did a computation, and in particular in this paper, and they showed that for rank 1 n equals 2 superconformal field theory in 2 dimensions, for which there is only 1-dimensional vacuum manifold, you can actually reproduce the large charge expansion, which you can, for example, compute from localization by writing down Coulomb branch effective field theory. Okay. So, however, this was done only for rank 1 n equals 2 superconformal field theory, or in the case of n equals 4 supermills, this was done only for SU2 gauge group. So the natural question that you might ask is what happens if you consider higher rank n equals 2 superconformal field theory, for example, n equals 4 supermills theory with higher rank gauge group. Unfortunately, not much has been explored. And there are, of course, reasons why not much has been explored, because there are several difficulties. First of all, in the case, let's say, let's consider contrast SU2 n equals 4 supermills versus SUN and SUM's n equals 4 supermills. Then, in the case of SUN n equals 4 supermills, there is a kind of variety of Higgs patterns. So in the case of SU2, when you go to the Coulomb branch, the SU2 gauge group automatically gets broken to U1 gauge group because of the Higgs thing. And on the other hand, if you consider SUN n equals 4 supermills and goes to the Coulomb branch, then depending on how you give a VEV, the gauge group sometimes gets broken to U1 times SUN minus 1, or sometimes gets broken to U1 n minus 1. So this U1 n minus 1 is normally what people call a Coulomb branch, EFT. But we need to keep in mind that depending on the way you give a VEV, the gauge symmetry might not be like this, but it might be like this. And the second difficulty is more technical. Because of a higher rank, because you have more fields, classification of supersymmetric higher derivative terms when you write down the EFT becomes more complicated. And so these are two difficulties concerning writing down effective field theory. And there is also a difficulty from the point of view of superconformal field theory. So in the case of SU2 gauge group, if you fix a charge and you declare that you consider some chiral primary, there is basically only one operator for each charge. And this is because of trace relation. For example, if you consider trace of phi to 2j, then if the gauge group, if the trace is taken over SU2 fields, then this is the same as trace phi squared to power j. However, that's not the case for SUN. And because of that, you can actually have a family of the operators for a given charge. And the last point is very, very technical, and it only I guess it makes sense for people who actually worked on this problem. But there is a way to get some correlation functions of these large charge operator from localization, but you cannot actually directly take the matrix model that's obtained by localization. And you need to perform what's called Gram-Schmitting procedure. And this Gram-Schmitting procedure also gets more complicated. But if you don't know what the details of this is, you can just forget about it. So, but here I want to emphasize that the point 1 and 3 are actually related. And I want to show that how they are related and in some toy model. Okay, so let's consider this toy model. So instead of considering superconformal field theory, I'm just going to consider zero-dimensional matrix integral. But I want to consider some matrix integral which has U1 charge. So because of that, I'm going to consider some complex matrix model. So this Z and Z bar are complex n times n complex matrices. And I'm going to analyze some two-point function of large charge operator, O and O bar. And I assume that O is made out of purely of Z, whereas O bar is made out of purely of Z bar. And for simplicity, I just consider it like a Gaussian matrix model. So this is a complex matrix model, which is much more complicated than the usual Hermitian matrix model, like a GUE or GOE. But there is a way to rewrite this matrix integral in terms of eigenvalue, thanks to the results by Dimitre. And this reduces to the following eigenvalue integral. So we have some integral over the eigenvalues, and instead of the usual fundament, we have some like absolute value squared, and then we have like an insertion corresponding to the operator O and operator O bar, and then I have Gaussian factor. So in order to see what's going to happen, let's consider a single trace operator, the O trace of Z to J, and insert it here. So O is this one, and O bar is the conjugate. And because we have two operators, we have two sums, and each sum basically corresponds to taking a trace. But because of U1 invariance, you can show that in this like a summation over two indices, only the term for which k equals L contributes to the final answer. So this reduces the double sum into a single sum, and the result we get is this expression. And furthermore, if you look at other factors, then you can see that other factors are completely invariant under the permutation of the indices J and K, which means that I can just replace this insertion of ZK to 2J by Z1 to 2J and just multiply a factor of n. So this, and if you take charge J to be very large, then you can see that this acts as a source when you determine the saddle point equation for this matrix eigenvalues. So this is what I wrote here. But the important point is that like this source term is only for Z1, which basically means that it's like it gives a VEV only to Z1, but treat other eigenvalues to be kind of like on the same footing. So this suggests that actually in this case, the symmetry gets Hicksed, the UN symmetry gets Hicksed down to U1 times UN minus 1. And so let's next consider some next simplest case, which is the double trace operator. So the double trace operator, so I take this one. And by doing the same analysis, now I can reduce it to a double sum, Zn to 2J1, Zn to 2J2. But so because I have like a two sum, and it seems like it gives a VEV to like two different eigenvalues. So you might think that, okay, so this should correspond to U1 squared times UN minus 2. But that's a little bit too quick because you really need to carefully decompose the sum into two parts. One for which n is not equal to n, and one for which n equals n. And for n equals m, again, the symmetry breaking pattern should be the same as before. So you get like a UN times UN, U1 minus UN minus 1. Whereas for this guy, you get UN breaking down to U1 squared times UN minus 2. So this basically suggests that if you just take some like a double trace operator, which looks very simple, then it's not going to admit a simple effective field theory description because it's going to correspond to a mixture of Hicksing patterns. And if you really want to kind of like get this Hicksing pattern, then you need to construct some nice linear combination, which is of this form. So this kind of explains the difficulty 1 that I showed is related to the difficulty 3. And so this argument can be generalized to other Hicksing patterns. And also here I was just talking about very, very simple matrix model. But conceptually or qualitatively, something similar happens also for n equals to general n equals to superconformal field theory. And one thing that I want to emphasize is that like by doing this analysis, you can of course like always construct some nice linear combination of operators which corresponds to a given Hicksing pattern. but general expressions are actually rather complicated. Okay, so any questions so far? Okay, so let me just proceed then. So, however, in the large n limit, there is a very, very nice basis. So far, like my discussion was valid for any like n. I didn't need to take large n limit, but in the large n limit, we know from the analysis of n equals 4 supermills and matrix models, there exists a very nice basis. So that's called sure polynomial basis, which is defined in this way. So the sure polynomial basis is labeled by Young tableau, and its definition is given by this. So Z is like a matrix valued field. So it has two indices, and you basically sum over permutation, and then you multiply the character corresponding to the character of the permutation group corresponding to the representation R. And I'm not going to explain why this is so, but you can just like check it by inserting these operators into the matrix integral that I showed, and taking the large n limit. And if you do so, you can see that there is a kind of like a very, very simple correspondence between the Higgsing pattern and the Young tableau. So which is as follows. So if you consider like a Young tableau, which consists of three rows, then the length of each row basically corresponds to the magnitude of source term for k's eigenvalue, which means that this Young tableau corresponds to the symmetry breaking pattern U1 times U1 times U1 times UN minus 3. And similarly, and the simplest case of this is just considering like a single row, and that corresponds to U1 times UN minus 1. And in fact, that's consistent with what I said 3 slides back, because in the large n limit, if you consider a single row Young tableau, this sure polynomial operator can be well approximated by the single trace operator. Okay, and the further nice thing about this is that this operator actually admits a very, very simple holographic description. So let's just discuss what the holographic description is. So now I'm really talking about n equals 4 supermills because I need to talk about some like a concrete holographic ADS-AFT correspondence. And so in n equals 4 supermills, this sure polynomial operator with a single row, which corresponds to the symmetry breaking pattern, Higgsing pattern U1 times UN minus 1, is dual to what's known as the dual giant graviton, which is a spherical D3 brane whose word volume is RT times S3, living inside ADS5. So this cylinder is ADS5, and then the D brane is like this. So and then like moving in time. And the size of this D brane is known to be given by J over N, which I denote by J. So J is the charge of the operator, where N is the rank of the gauge group. And if you take, so this is the holographic description of this operator. And what's nice about this holographic description is that you can actually see the emergence of large charge expansion also from the holographic side. So if you take the large charge limit, which is like a J going to infinity limit, then this D brane, spherical D brane, like become bigger and bigger, and it eventually approaches the ADS boundary. And if it approaches the ADS boundary, originally, although it was like a spherical D brane, it can be well approximated by a flat D3 brane because it becomes very, very large. And this flat D3 brane is nothing but the D3 brane, which effectively describes or holographically describes n equals 4 supermills theory on the Coulomb branch. So in other words, so this holographic description basically gives you a geometrical realization of the large charge expansion. And this curvature expansion basically corresponds to 1 over J expansion. And furthermore, the dBi action determining this excitation of the D brane, or like a low energy EFT on the D brane, can be identified with the large charge EFT. So this is the basic picture and how to understand the large charge expansion from the holography. But I should also admit that so the explanation I gave now is just at this moment qualitative, and there are lots of work that one can try to perform. For example, like making a precise comparison between the DBI action and the large charge EFT, and that hasn't been done, and it's probably an interesting question to address in the future. Okay, so let me also say one thing. So this deep brain picture is of course is coming from the holography. So this is basically valid for any n large n limit, but DBI action for spherical DC brain has actually various nice features. That's also true for series without large n limit. For example, it realizes the supersymmetry correctly, and it also, as I said, it realizes the geometric realization of the large charge expansion. And furthermore, it nicely incorporates for a manifest S duality. So although this original DBI action is expected to describe the large n and large lambda limits, well, actually large lambda is also important if you want to neglect the alpha prime correction to the DBI action. But there might be a chance that it also captures some important aspects of, for example, just SU2 n equals 4 super mils, which is very far from SU n equals 4 super mils in the large limit. And this is of course again, this is more like a conjecture or a suggestion, and it's probably important. It's definitely important to work out the details. But I should mention that as something similar was discussed in the past by John Schwartz in the context of Coulomb branch effective action. And he basically conjectured that the DBI action of the flat D brain, D3 brain, can capture some important aspects, or maybe it captures everything about low energy effective action of SU2 n equals 4 super mils. But of course, more work, and what I'm saying is kind of a large charge version of that. But of course, more works are needed. Okay. Any questions so far? So let's now discuss something else, which is about double scaling limit and the central extension of the symmetry. So this part is based on the work in progress with Ethan Wan and Joel Caetano. So far I've been talking about holography, but now let's get back to the rank 1 series. So now you can, I have in mind SU2 n equals 4 super mils, for instance. And so before I explained that people analyze a large charge expansion of n equals rank 1 superconformal field theory using Coulomb branch effective field theory. But because some quantities, for example, 2-point function of large charge BPS operators can be computed by localization, people actually can go beyond one over J expansion by taking the localization result and expand. And if you do so, you actually start seeing some exponential corrections on top of 1 over J expansion corrections. And the physical explanation of these exponential correction is that they basically come from some massive BPS particles in flat space. So which are not necessarily included in the Coulomb branch low energy effective action, because Coulomb branch low energy effective field theory only describes the dynamics of massless particles. And those massive BPS particle, if those particles are exchanged, we typically get this kind of Yukawa-like term. And if I translate that to the charge and the GM mils, in the case of n equals 4 super mils, we get this factor which precisely matches this factor. And furthermore, because of this structure, their contribution, so there is one interesting limit in which their contributions get enhanced, which was first analyzed or discussed in this paper. And that's called the double scaling limit. So this is a bit interesting limit. So this limit is a bit like a 't Hooft limit, But because here we are talking about SU2 n equals 4 supermills, so we cannot really take a usual to Foote limit, but you can still take this limit where j is infinite and g mills times square root of j is fixed. So in other words, like j is playing the role, the charge j is playing the role of like a rank of the gauge group in the usual to Foote expansion. So in this limit, so these massive BPS particles, the contribution from those particles are enhanced and becomes order 1. However, one thing we need to be careful about is that, but before talking about some subtle points, let's just remind you what the BPS states in flat space are. So as you probably know, the BPS states in flat space are basically short multiplet of some centrally extended Poincare supersymmetry. So this is the usual like extended supersymmetry algebra. So Q and Q dagger commutes to momentum translation. But in the extended SUSY series, you can also consider like a anti-commutator of Q and Q, and it can have non-trivial central extension. And the BPS operator, BPS states, which lives in the short multiplet, satisfies the BPS bound, which basically satisfies mass is equal to Z. And so those states that are that's responsible for the exponential fractions are described by this flat space SUSY, extended flat space SUSY. And this use of flat space SUSY is certainly justified in the usual large charge limit, because in that limit, mass of the BPS particle is given by Gm mills times square root of J. But in the usual large charge limit, we fix Gm mills and take J to be very large. So this is really, really small. And which is basically says that this is much smaller than the size of the sphere. So the BPS particle doesn't see the curvature of the sphere. So that's why we can use the flat space SUSY. However, the use of this flat space SUSY is not really justified in the large double scalar limit, because if you evaluate or estimate mass of BPS particle directly in the double scalar limit, then it's going to be given by some, well, again, the same expression, but now because of the double scalar limit, this is actually order 1. So the BPS particle should know about the curvature of ADS. So then you can ask the question, what is the symmetry governing this limit? So if that is not the flat space supersymmetry. And there is actually a very simple answer to this question. So the relevant symmetry, especially for n equals 4 supermills, is what's known as centrally extended SU2/2 square symmetry. So this symmetry, SU2/2, is a part of the superconformal algebra. And in particular, it includes some rotation on the of the sphere. And so it knows about like the curvature of the sphere. And the algebra is given by this expression. So Q are basically like a supersymmetry, and S are superconformal symmetries. And so let me just first like say the claim, and then like in the next slide, I'm going to explain how to understand it. But let me just first make comment that the same symmetry actually was first used by Weisert in the analysis of large n equals 4 supermills, which is like n equals infinity and Gm square n fixed. But here we are in a completely different limit, which is like a large charge double scalar limit. But still, we see that the same symmetry actually plays an important role. So let me just give you a very, very brief sketch of the derivation, why we expect this symmetry to appear, especially why this central extension to appear in this limit. And the derivation is actually very, very simple. So let's remind us like the SUSY transformation of n equals 4 supermills, or more generally n equals 2 superconformal field theory. So as we all know, if you act the supersymmetry on the boson, you get fermion. And if you add the supersymmetry to the fermion, you get boson. But on top of that, you in the gauge theory, you also get this term, which is given by the commutator between the scalar field and the boson. And it comes with Gm mills. This basically means that if you consider some kind of like if you act supersymmetry twice to the boson. So this Q square is not really like a same Q square. It's more like some choice of different Qs. Then that's going to give you this expression, which is a commutator of scalar field with some boson. And in particular, by choosing appropriate Qs, you can take this phi to be the phi which gets a VEV because of the large charge presence of the large charge operator. So in the case of SU2, it often gets a VEV like this, diagonal in Cartan. And so if you take the commutator and especially look at the off-diagonal component, you can see that if you do this, then you get some 2 times V times G Hamilton boson. So if you consider the action of Q square on this off-diagonal component, then actually the anti-commutator of Q and Q is non-zero, and it gives you some like G Hamilton times V, where V is proportional to J, where J is a scalar, where J is a charge. And so, and furthermore, on this like a cylinder quantization, the Hermitian conjugate of Q is given by superconformal generator S. So by requiring the consistency, you can also show that the anti-commutator of S and S is given by V dagger. So S and S is also non-zero. And by completing this algebra, you can actually derive the centrally extended symmetry, which was originally derived by Kaiser. Okay, so here, so I just made a claim that massive excitation in the double scalar limit is governed by the centrally extended SU2/2 square. And in particular, it's given by some short representation of the centrally extended SU2/2 square. And you can ask now whether it is useful or not. And it's indeed useful. It's useful because you can use it for the classification of excitation on top of the large charge state. And it's also useful for determining the dependence on this like a large charge to fluid coupling, which we take to be finite in the double scalar limit. And for instance, this is first analyzed in the usual context of large N limit by Bizard, but you can apply the same analysis to here, and then you can determine the energy of the excitation as a function lambda at all order in lambda. And furthermore, we expect that 1 over J correction can be determined by SU2/2 invariant S matrix, which was again originally proposed by Bizard in a different context in the large N limit. Okay, so let me just make several comments. So large charge expansion relates centrally extended Poincare-Suzy and SU2/2, and this Poincare-Suzy is a particle, is a Suzy that governs a particle, whereas SU2/2 is more like knows about the sphere, so it's more like operator, the symmetry for the operator. So in some sense, the SU2/2 is the S3 extension, S3 version of the Poincare-Suzy. And okay, let me just skip these 2 points, and then I wanted to say that similar story exists also for n equals 2 superconformal field theory, but in that case we don't have SU2/2 square, but we have a single SU2/2, but again it's going to be centrally extended. So any questions so far? Okay, so let me now move to the final topic, which is about the correlation function of deep brains. So in this last chapter, I'm going to talk about slightly different things. So instead of talking about what the large charge expansion is for n equals 4 certain mils, I'm going to get inspiration from the large charge expansion and use it to kind of resolve some puzzle in the holography. So to be concrete, let's first give you what I'm going to talk about in this chapter. So I'm going to talk about the 3-point function of 2 large charge operator and 1 light operator. And all of them are assumed to be BPS. And so by large charge, I mean J is of order n, where n is the rank of the gauge group. and where K and L, like the difference between these large charge operators and this like a charge of this light operator is assumed to be of order 1. And more concretely, I am going to talk about some specific Shota polynomial operator, which corresponds to a single column operator. But the details are not so important. Whereas the light operator is, as I take it to be, a single trace operator. And now, and also importantly, I'm now working in the usual foot limit. And we know that what the holographic description of these this 3-point function is. So this large charge operator, dj and dj plus k, is known to correspond to some d-brane. So if you have 2 of these guys, then there should be some like a classical trajectory of the d-brane, which is very heavy. And whereas this third operator, which is light, corresponds to supergravity fluctuation. So it emits some like a supergravity fluctuation, and it hits this like a classical heavy d-brane. And this 3-point function was analyzed on the supergravity side by these people back in 2011. And they basically proposed the following result. So they basically proposed that this 3-point function should be given by some perturbation of the dBi action described in the d-brane. And the rough idea is that, so originally we have like a dBi action. If you just have like a 2 large charge operator, but what we really want to study is the reaction of this d-brane when you further perturb it by the supergravity fluctuation. So that's why we basically need to perturb the dBi action by this supergravity fluctuation. And the structure of the supergravity fluctuation is essentially determined by the bulk boundary propagator. So because we are inserting some operator here, so x0, so the metric gets perturbed in a way which is proportional to bulk boundary propagator. And there is also some fluctuation for the spherical harmonic, like S5 factors. And so this was analyzed in the past, and they encountered one important problem, which is as follows. So if you look at this 3-point function from the n equals 4 superconformal symmetry, we know that it is protected, by which I mean like it's independent of the coupling constant. So we should be able to directly compare the results of the field theory at weak coupling to the results computed from holography, which corresponds to strong coupling. However, what they found is that the result from holography didn't match the result from field theory, even for the simple case of k to 0. And it turns out that they missed 2 important effects. One is called orbit average, and the other is called wave function contribution, both of which are well known to large charge community. So let me just describe what they are. So in order to describe what they are, it's useful to consider some like a simple toy model, which is quantum mechanical toy model. So let's consider a quantum mechanical toy model, which is defined on S1. So this theta varies from 0 to 2 pi. And we further assume that there is a U1 symmetry of shifting theta by constant. And in this quantum mechanical toy model, so this theta is the variable, I want to compute the overlap between some heavy state with charge J and J plus K and some light operator in the semi-classical limit in which J is infinite, H bar is 0, but H bar J is fixed. To analyze that, it's useful to write down the path integral. So this is the path integral. You do the path integration over the variable theta, and this is the wave function corresponding to this state, and this is the wave function corresponding to this state, and then you have insertion of the operator and the action. And because we are taking this limit, we expect that this can be approximated by the saddle point, and that's going to give you this expression. So this is the expression that I wrote in the previous slide. However, this expression is actually incorrect. And the reason is very simple. Because of U1 symmetry, which allows us to move theta by a constant amount, if you find one solution theta 0, then we can immediately construct a family of saddle point solution. So in other words, the saddle point is not isolated. So there is a family of solutions parameterized by C. So in those cases, we need to modify the WKD saddle point expression, and we instead need to kind of average over C. So this was kind of discussed in a different context by these people. And the correct result is going to be given by this expression. So you need to integrate over C, and you insert like a saddle point, which is given by this. And if you further use the fact that action is invariant under the shift, then this can be further simplified to this expression. And the rest is given by this. So this e to ik minus ikc comes from the mismatch between this and this. And then we have some operator insertion, and we have integration over C. So this integration is precisely what I call the orbit average. And whereas this part is the wave function contribution, which is the second contribution that they are missing in the literature. So basically, this quantum mechanical toy model basically captures everything. And what we just need to do is to apply this method to the holography or D-brane that I described. So also in this holography setup, we expect the final answer is given by some semi-classical configuration of the D-brane. So we first write down or assume that there exists some path integral over the world volume coordinates of D-brane, and that there is a wave function and operator insertion corresponding to this light operator, and then wave function for this guy, and then there is a DBI, and this is a minor term. And then what's important is that, like again, also in this case, we need to do the average over some parameters. So in the previous case, there was only a single symmetry, which is U1 symmetry. But in the case of BPS operator, they come with two non-zero charges. One is a conformal dimension, the other is U1R charge. So we need to integrate over both. So this is so basically we first construct one solution, saddle point solution, and shift the parameters corresponding to delta and J and average over it. And the wave function factor is given by a similar expression as this one. Yeah. And in this case, because we have two symmetries, we have like two plane wave factors. And taking this expression and by shifting it, you can see that like there is some extra contribution because of the shift. And combining everything, we arrive at this expression. So this is again the realization of the orbit average, whereas this is coming from the mismatch of the wave function. And finally, there is of course like this factor, which corresponds to the operator insertion. This operator insertion is basically the same as what they discussed, because this describes the perturbation of the supergravity fluctuation coming from the supergravity fluctuation. And if you combine everything and do the integral, and actually this is a little bit complicated integral, and the final answer is given by a rather complicated expression, which involves the hypergeometric function. But surprisingly, this complicated expression is in perfect agreement with the field theory, namely tree level computation in n equals 4 dependence. But I should emphasize that the way which arrives at this expression in holography and gauge theory is completely different. So let me just make several further comments. So this computation can be generalized to other setups like ADS 4 times S7 over ZK, which corresponds to ABGM in the M theory limit, or ADS 4 times CP3, which also corresponds to ABGM, but in the foot limit, and possibly more. And in particular, if you consider the ABGM case, the expression is further complicated, and it's given by this super complicated expression. And for ADS 4 times CP3, which corresponds to ABGM theory, three-point function of BPS operator is not protected. So we cannot really take this answer and compare it with the gauge theory answer. So in order to really test if this prediction is correct or not, we need to develop some non-perturbative approach like integrability And that's what we are doing right now, and we hope to get the results very soon. Okay, so I'm almost running out of time, so let me just conclude. So what I did here is some, so let me just summarize what I explained today. So I explained that large charge BPS operators for higher rank superconformal field theory is a bit more complicated because of the degeneracy. And in order to resolve the degeneracy, you need to compute, well, because of this degeneracy, in order to have a nice effective field theory description, you need to consider some linear superposition of the operators. And in the holographic theory or large unit theory, there is a simple basis which realizes this, and that's called the Shota polynomial basis. And the simplest one, which consists of single row, is holographically due to spherical D-brane. And this holographic point of view basically gives you the geometric realization of the large charge expansion. And second, I talked about double scaling limit, and I explained that the double scaling limit of superconformal field theory is governed by some centrally extended SU2/2 symmetry, which also shows up in n equals 4 supermills. And finally, which also shows up in n equals 4 supermills in the Toput limit. And finally, I described the correlation function of D-branes, and I emphasized that the orbit average and wave functions are important. And the natural question after this analysis is that, can we apply this idea to operators which are even heavier than D-branes? And what happens if the operators are heavier? For example, what happens if the operators correspond to deformed geometry like LLM geometry? I can make some comments if somebody asks the question, but let me just end here. And well, I can also comment on this slide if somebody asks, but let me just end here. Thanks a lot.
Thank you. Are there any questions?
I have a rather simple question. So at the beginning, you mentioned this law, J to D over D minus 1 plus correction.
Yes.
So this law gets violated whenever you have supersymmetry. But whenever you don't have supersymmetry, can you reproduce it holographically in some of the examples?
Right. That's, yes. The answer is yes. Okay, so I should use this feature. Yeah, that's a very good question. And basically, there's only one paper which discusses this, but the answer is yes. I'm not sure which page.
You mean the leading behavior or the subleading, the first subleading as well?
Okay, so this paper analyzed ADS RN black hole, and when the size of the black hole is very large, and they first reproduced the leading behavior, and they also confirmed that there is a correction suppressed by 1 over J, but of course, like the coefficients depend on the details, because it also depends on the the coefficients of the EFT. So they didn't make any further comments about it.
Ah, okay, thank you. Mm-hmm.
Other questions? So I wanted to ask, like like in the middle of your talk, there was some kind of relation between the shape of Young diagram and yeah, you discussed operators labeled by Young diagrams, and you said that they correspond to some D-branes, and you considered symmetric case.
Right.
And what are the D-brane properties that correspond to like mixed symmetry? Is it
okay? So let's first discuss this case. Like I only discussed this one, right? So so this one is actually easy. So because each one corresponds to some D-brane, and the length of the row corresponds to the size of the D-brane. So if you want to analyze this, then it's going to be given by holographically, like 3 concentric D-branes.
I see.
And so you can like, yeah, You can also add more rows if you want. But what's funny is that there is like completely different description for the totally antisymmetric representation. The totally antisymmetric representation is very hard to interpret from this point of view, right? Because like it's a bit like having like a very, very tiny deep brains. Like And it turns out that object also has a dual description, but now it's going to be be given by some D3 brain, which is point-like in ADS, but it's extended in S5. So this one is extended to ADS5, but the other one is extended in S5.
I see. And I don't know, I missed a bit, like what was the difference in the setup in the second part and in the first part? So in both cases you have large G, but then in the second part you have some fixed combination.
Yes. So the first part is really about large N limits. So it's about, so the first part is about like a really like a GML square N fixed and N infinity. And then I was further taking J over N to which is J to infinity. And then expanded in powers of 1 over J. But in the second part, N is really 2 because I considered SU2 series. And then instead of, so we cannot really like fix this object. And instead I fixed GML squared times J to be finite value. So it's a different limit.
Okay. And can you get some information for operators with low scale dimension?
By doing the large charge expansion, you mean?
Yes.
Yeah, that's an interesting question. I think people actually analyze that in the context of some like a generic conformal theory without supersymmetry. And surprisingly, people found that like a large charge expansion, let's say like take this and this, accurately describes some of the dimension of the operator of order like a 1. There is no reason why that's true, but like experimentally they found that's true.
Thank you. Any other questions?
Maybe tiny little question. So there must be some overlap between the integrability and this large charge expansion, right? So where you can compute from both sides and literally compare, and maybe even prove that something is identical rather than.
Yeah. Okay. So that's a very interesting question. So let me just say something. So one thing, one situation in which we can try to use integrability is to, so here I discussed this operator. And so I can imagine considering some like a 3-point function of this operator, Z bar, and this operator. And both of them are given by D brain. And then single trace operator, some like a non-BPS. And try to compute it from integrability, for instance. And then take the limit where J is infinite. And on the other hand, I can try to directly compute non-BPS operator, expectation value of the non-BPS operator on the Coulomb branch. And I'm not sure if this is precisely what you're asking, but in principle, we can just, if we succeed in computing both objects using integrability, then by taking large J limit and comparing the answer, we can actually see if this notion of large charge expansion is really correct or not for like even for non-BPS operator.
Yeah.
And certainly integrability, if it's applicable to this side, then it also knows about like all the 1 over J expansion as well. And the leading one is just given by Coulomb branch, flat integral.
Yeah, okay. Thank you.
Any other questions? Okay, it seems that we don't have any other questions. So thank you very much for a nice talk. And thank you
Great.
everyone for
Yeah,
coming.
thanks a lot. Yeah, thanks a lot.